In our last lecture before test 2, we're going to talk about matrices. In our last lecture, previous lecture, we talked about vectors. We talked about the length of a vector, what is a vector, how do we add two vectors, how do we scale a vector by a real number, and we talked about the dot product and the geometric information that the dot product conveys, particularly about perpendicular vectors. So today we're going to talk about matrices, and I'll go ahead and say and linear systems. So let's say that Jack owns a bike shop, and in Jack's bike shop he sells bicycles and he sells unicycles. So the bicycles each have two wheels, obviously, and the unicycles each have one wheel. Let's say if Jack looks around, he can see that he has number of wheels is, let's say, 150, and number of, let's say, objects, meaning either bicycles or unicycles, is, let's say, 100. So the total wheels in his store is 150, but he has, counting bicycles and unicycles separately, he has 100 of those. Some of them are bikes and some of them are unicycles. So I want to say let X be the number of bikes and let Y be the number of unicycles. And well, every bike has two wheels, so if you have X bikes, they have 2X wheels, and every unicycle has one wheel. Right? And well, the number of objects, that's just X plus Y. Right? X bikes plus Y unicycles is the 100 objects that we have here. So this is a linear system. We could say a linear system of equations. It is a system because there's more than one. It's linear because each have some constants here, and here I have linear functions of x and y. So when I say linear, it's not x squared, it's not x times y, it's not sine of x or anything like that. It's a constant multiple of x plus a constant multiple of y. I could have linear equations with x, y, z, w, x, y, z, and more than just two variables. But the linear here refers to the fact that these equations are linear in the variables x and y. This is a linear system. There are a few different ways to solve linear systems. So we can solve a linear system by substitution. Okay. So by substitution, we mean I want to take one equation, solve it for one of the variables in terms of the other variable, and then plug that into the remaining equation. Okay, so let's say 150 equals 2x plus y. Therefore, y equals 150 minus 2x. Okay, so I took one equation and I solved in that equation, I solved for y in terms of x. And now what I can do is take the other equation, 100 equals x plus y, and now from over here I know that y equals 150 minus 2x. So this is x plus 150 minus 2x, because this part is y. And I figured that out over here. So I get, if I simplify, the left side is still 100. On the right side I'm going to have 150 minus x. So x minus 2x is minus x. And here I figured out x equals 50. Okay. And now I take that, put it back over here. Y equals 150 minus 2 times 50, which is 150 minus 100, which is also 50. So x equals 50 and y equals 50. So I have 50 bikes and 50 unicycles. And if I look back up here, I can check. 50 bikes plus 50 unicycles is 100 objects. 50 bikes is times 2 is 100 wheels on the bikes, and 50 wheels on the unicycles. That's 150 wheels altogether. So I can check my solution by plugging the x, y values in here and seeing that I do get 150 on the first equation and 100 on the second equation. And this is substitution. The idea behind substitution would be the same, even if we had 3, 4, 5 variables, more than two equations, more than two unknowns. So as a general principle, if you want to have a solution here, if you expect to have a unique solution, then you typically expect to have, well, here I have two unknowns, x and y. I expect to have two equations. Okay, so there are a lot of very subtle things here where I don't necessarily need in equations and in unknowns. I might have some extra superfluous equations, or I might have some equations that contradict each other and there's no solution. And if you want to learn more about that, you have to take the full linear algebra course. So linear algebra is one of my favorite courses, so I highly recommend that. It's also one of the most useful courses I've ever taken, particularly as someone who does a lot of statistics. Linear algebra, being able to deal with matrices is hugely important. Right. So here in this process, we didn't say anything about matrices. So let's talk a little bit about matrices. So a matrix is an array of numbers. And a matrix is an array of numbers, so it feels kind of silly to write down examples, but say 1, 2, 3, 4. Right? This is a matrix. Okay, it's gonna have 1, 2, 4, 7, 9, negative 1. That's a matrix. 0, 0, 1, 0, 1, 1. Right? This is a matrix. So matrix has rows and columns. Right? So this matrix has two rows, row 1, row 2. It has two columns, column 1, column 2. This next matrix has 2 rows and 3 columns. This one has 3 rows and 2 columns. So if the matrix has m rows and in columns, we say the matrix is m by n. Okay, so m by n, m is the row number, n is the column number. So here this is 2 by 2. This one is 2 by 3, 2 rows, 3 columns. This one is 3 by 2, 3 rows, 2 columns. So we can do the usual things with matrices. We can add and scale. Right? So we add matrices, we just add corresponding entries. So let's say 1, 2, 3, 4 plus 2, 2, 2, 5 equals, well, if I have a 2 by 2 matrix and a 2 by 2 matrix, I'm going to get a 2 by 2 matrix. In the top entry, I take the top left entry in each. Okay, so 1 plus 2 is 3. Now for the top right over here, I'm going to add top right and top right here, so I get 4. And then I add 3 and 2, which is 5, and then I add 4 and 5, which is 9. So these two things give me that entry. These two things give me that entry, etc. So just like with vectors, I add corresponding entries of the matrix, and that gives me the resulting entries of the sum. Okay? So in order for me to be able to add two matrices, they have to have the same dimension. They have to have the same m and n. So this is 2 by 2, this is 2 by 2, I get a 2 by 2. If I have a 2 by 2 matrix and a 3 by 3, I can't add them. There's no definition of addition of matrices that don't have the same numbers of rows and columns. And I could also scale a matrix. This is pretty easy. So let's say 1, 2, 3, 4 times the scalar 3. I'm going to have, this is 2 by 2, so I'm going to have 2 by 2, and I'm going to multiply everything by 3. So 3, 6, 9, 12. So I just multiply each individual entry by the 3. If I want to take a matrix and multiply it by a scalar, I just multiply each individual entry by the scalar. Okay, so addition, scalar multiplication are completely straightforward for matrices. So, what about multiplying a matrix by a matrix? This is the part that's not straightforward. We can multiply matrices with the right dimensions. Okay? So, if A is, say, P by Q, and B is m by n, then the product AB is defined if and only if Q equals M. So the number of columns of the first matrix has to be equal to the number of rows of the second matrix. Now here, as we'll see in just a moment, matrix multiplication is not commutative, which means that if I have two matrices and I have AB and BA, if both of the products AB and BA are defined, they're not necessarily equal. Okay? So the order, so this is A times B, this is not B times A, and that order is very important for matrix multiplication. Okay? So I'm going to say A, P by Q, and B, M by N. If I want this multiplication to be defined, these two numbers that are touching each other have to be equal, right? Those numbers have to be equal. And then I'm going to get a matrix over here, and the dimensions, well, the number of rows over here is going to be the number of rows over here. Okay. And the number of columns over here is going to be the number of columns over here. Okay. So this is the way that the dimensions have to work for matrix multiplication. If I want A times B to be defined, then the number of columns in row A has to be the same as the number of rows in matrix B, and then the product will have the same number of rows as A and the same number of columns as B. Right? So so let's talk about matrix multiplication. How do I find the entry in the ith row and jth column of the product? Okay. So I have A over here and B over here, and then I have a product, which I can call C, and I want to know, how do I find out what C actually is? So I want to know the entries of C. Okay, so C is going to have an entry in row I, column J. So I need to know, how do I find these entries over here? And we'll do a concrete example in just a minute because it is pretty abstract. But I take row I in the matrix A, and then I take column J over here, and now I take the dot product. And that is the entry that goes in row I, column J of the product. So I take this row here and this column here, and I take the dot product of those things. If you remember the dot product, we talked about it in the last lecture. It means I'm going to take the first thing here, multiply it by the first thing here, and the second thing here, multiply it by the second thing here, and I keep going all the way till I get down to the last thing here and the last thing here. So I'm going to multiply the things in this row by the things in this column. First thing by the first thing, second thing by the second thing, etc. And then I'm going to add all those together, and that's what this dot product is, and that's entry, the entry in row I, column J over here. Okay, so if A has Q columns and B has M rows, and Q and M are the same, then this row is going to have Q things in it, and this column is also going to have Q things in it. So the length of this row is the same as the length of this column, and this dot product is defined, and that's the reason we need Q and M to be equal here. So let's do a specific example. Let's say 2, 3, and then 1, 4, and then 1, 5, negative 1, 4. Okay, so so first I'm going to go and figure out what goes in row 1, column 1. Okay. So I have these matrices A and B. They're 2 by 2, so this is defined, and the result is going to be 2 by 2. So I'm going to have 2 by 2 here, and then 2 by 2 here. These inside numbers match, so I can multiply the matrices, and then the result is going to be 2 by 2. Okay, that's how the matrix multiplication works. So I'm going to look at row 1, column 1. So what I'm going to do is I'm going to take row 1, which is 2, 3, and column 1. Right, so I take row 1 from this matrix and column 1 from this matrix, and I'm going to do the dot product, which is, I do the first thing here times the first thing here, which is 2 times 1 plus 3 times negative 1. Okay? So this is 2 minus 3, which is negative 1. Okay? So I took row 1 here and column 1 here. I took the dot product, and I got negative 1. And now that negative 1 goes in row 1, column 1 of the product. Okay? Now I'm going to do row 1, column 2. So I'm going to do row 1 again from the same matrix, 2, 3. Now I'm going to do column 2, which is 5, 4. I'm going to take the dot product, which means the first entry here by the first entry here, which is 2 times 5, plus second entry here times the second entry here, which is 3 times 4. This is 10 plus 12, which is 22. Okay? So that goes in row 1, column 2 of this matrix. I'm going to do row 2, column 1. I'm going to have 1, 4, 1, negative 1. I'm going to do the dot product. And I get 1 times 1 plus 4 times negative 1. And it's 1 minus 4, which is negative 3. And that negative 3, okay, so I took row 2, column 1. I took the dot product, which is the first entry here times the first entry here, second entry times the second entry, and then I add those together, I get negative 3. And this negative 3 goes in row 2, column 1 of the matrix. And so for the last row 2, column 2, I'm going to do 1, 4, that's row 2 from the matrix here, do column 2, so we get 1 times 5 plus 4 times 4, which is 5 plus 16, which is 21, and that 21 goes here. Okay? So this is my matrix multiplication. Okay, so every row here, dot product every column here, and then row I, dot product with column J, gives me the number that goes in row I, column J of the product. This is matrix multiplication. You might ask, why do we do matrix multiplication this way? Well, a very common thing, well, so let's do it this way. So a vector is a matrix. Right? So a column vector, so remember we talked about row vectors and column vectors. Okay? So a column vector is a matrix with one column. So for example, I could say 150 and 100. Okay, this is a column vector. Okay, and it is a 2 by 1 matrix. Okay, so you notice here sometimes I use parentheses, sometimes I use the square brackets for matrices. Either one works. So I'm being inconsistent here. Feel free to be inconsistent in your own work. So why might we want to use matrices, or how can we use matrices to solve the same kind of problem that we worked earlier? Well, if I take, let's say, x, y times 2, 1, 1, 1, right. This 2, 1, 1, 1, this is a 2 by 2 matrix. This x by y is a 2 by 1 matrix, 2 rows and 1 column. Right? So this multiplication is defined, right? Because the two numbers here are equal, and I'm going to get a 2 by 1 matrix. Okay? So I take row 1, dot product with column 1. Here there's only one column in this xy matrix. Right? So I have, so I'm going to get a 2 by 1 matrix. The first entry, the entry in row 1, column 1, is going to be dot product 2 times x plus 1 times y. Okay. And then the dot product 1, 1 dot product with xy gives me x plus y. So I don't need this 1 here anymore. So this is the, well, it's another column vector, but it's also a 2 by 1 matrix. The first entry is 2x plus y. The second entry is x plus y. Now, if I set this equal to 150 and 100, now when I set matrices or vectors equal to each other, it just means corresponding entries are equal to each other. So if I have this vector equals this vector, that means 2x plus y equals 150 and x plus y equals 100. And if you remember, this is the same thing that we had in our system of equations on the first page. Right? So I have a matrix equation and because matrix multiplication works this way, this matrix equation is the same as this system of linear equations. So now I only have one equation, but it's an equation with vectors and matrices instead of equations with numbers and individual variables. Right? So now when we can take the linear system that we had earlier and express it in this matrix notation, and then we have all kinds of nice tools from linear algebra for how to solve matrix equations and how matrix equations work and things like that. We will not get into most of that, but we can. Okay, so we can do one interesting thing. So if A is a square matrix, and what that means is number of rows equals number of columns. Right? So obviously a square matrix has the same number of rows and columns if it's going to be a square. So a square matrix is invertible. So let me write that so that it's actually readable. Invertible if there exists a matrix B such that AB equals BA equals I, where I is this matrix that has ones down the main diagonal and zeros everywhere else. Okay. So if A is a square matrix, that means the number of rows equals the number of columns, so we could say it's n by n. And if AB and BA are both defined, that means B also has to be n by n. Okay. And then here, if I do the product is going to be n by n. And so the number of rows and columns here is n, whatever that is. Okay. And down this main diagonal, I have all ones and then zeros off the main diagonal. So this is a little abstract. So this I matrix is called the identity matrix. If I want to be specific, I can say IN. Is the 2 by 2 identity matrix is not the same as the 3 by 3. It's not the same as the 4 by 4, etc. So this identity matrix plays the role of the number 1. Okay? And this B plays the role of the reciprocal of A. So for example, right? So if I want to say AX equals B, where A and B and X are just real numbers, not matrices or anything, and A is not equal to 0, then I can solve by multiplying by the reciprocal. Okay? So I can figure out B. Now if I have, let's say, AX equals B, so if I have a matrix equation like this, where A is some square matrix and X and B are both vectors, then if BA equals AB equals this identity matrix, then X equals the identity matrix times X. Okay, so here is a fact about the identity matrix, is if I multiply any vector by the appropriately sized identity matrix, it's just the same as multiplying by 1. So the identity matrix times X is just X. That's the property, the kind of defining property of the identity matrix. This is equal to, let's see, B times A times X, and this is equal to B times, well, if AX equals B, then this is equal to B times B. And if I happen to know what B is, right, in our bike example, I knew what B was. It was 150, 100. Okay? And if I know what A is, which I did in that example, A was the, so here, in this example, this is B, and this is A, and this is my vector X. So, if I know what A is, in the previous example it was 2, 1, 1, 1, then I can find, at least in principle, the inverse matrix B, and then I can multiply and figure out what this is. And I can solve for X just by simple multiplication. Okay? So, let's see. So, so this is what we had earlier. This is the exact same thing as our bikes and unicycles example. The answer was X equals 50, Y equals 50. Right? So that's what we should get here. So this is A, and this is our vector X. Maybe I should put an arrow over it to indicate that it's a vector, so we don't get confused between the vector X and the number X. And then a vector over here that I'm going to call B, again with an arrow over it. Okay. How do we find the inverse of a 2 by 2 matrix? So I'm going to say more about this in a minute, but what I'm going to do is I'm going to do so what I do is I take the 2 and the 1 and I switch places with them. Okay. So here I have a 2 and a 1, and I switch places. Okay? And now these other two things, I multiply by -1. So here I get a -1 here, -1 here. So this 1 here becomes a -1 in the top right. The 1 in the bottom left here becomes a -1 in the bottom left here. And now, what I'm going to do is I'm going to divide by this special number. So I'm going to take the product of those two things, which is 2 times 1. I'm going to take the product of those two things, which is 1 times 1, and I'm going to subtract. So here I get 1, -1, -1, 2, and 2 times 1 minus 1 times 1 is 1. So this is the inverse. And I'll explain to you what I did there with a formula in just a minute. But here's my inverse. And let's check that this is the inverse. Okay, so I'm going to have 1, -1, -1, 2 times 2, 1, 1, 1. Okay, so this is B times A. And this should be the identity matrix. Okay? So remember, the identity matrix is from the top left to the bottom right is going to have 1s and then 0s everywhere else. Okay. So what I do here is I take row 1 times column 1, and I get 1 times 2 plus -1 times 1. That's row 1, column 1. Row 1, column 2 is going to be 1 times 1 plus -1 times 1. Okay, so row 1 here times dot product column 1 here. Row 2 dot product column 1 gives me the entry in row 2, column 1. So I'm going to get 2, -1 plus 2, 1. Okay, that's row 2 dot product column 1. Row 2 dot product column 2, I'm going to have -1 times 1 plus 2 times 1. And this is, well, that's 2 minus 1, which is 1. That's 1 minus 1, which is 0. That's -2 plus 2, which is 0. And this is -1 plus 2, which is 1. And this is the 2 by 2 identity matrix. So B times A gives me the identity matrix. Now, I can also multiply, so I should also have So this is the identity matrix, the 2 by 2 identity matrix. So here I should be able to do A times B and also get the identity matrix. I'll leave that for you to do. But here I'm verifying what I'm doing here. The purpose of this is to verify that this B is actually the inverse of this matrix A. Okay, so let's check how we might use this. So what I have is xy equals 1, 0, 0, 1 xy, and you can check here, actually do this multiplication. Right? So I do row 1 dot product with this column, and I get 1 times x plus 0 times y, which is x. And then I do row 2 dot product column 1, and I get 0 times x plus 1 times y, which is y. So you can check this multiplication. Multiplication by the identity doesn't change the vector. Okay? So now I'm going to get b, which was 1, negative 1, negative 1, 2, times a, which is 2, 1, 1, 1, times xy, because this part equals 1, 0, 0, 1. We actually did this multiplication on the previous page and showed that this matrix is the identity. Okay, so these two things are equal because this matrix multiplication is that matrix. Okay? But now, this part from the previous page, this 2111 xy, should be equal to 150, 100. So this part should be equal to 150, not over 100. So this part, if xy is actually going to solve the system, this part should be equal to b, and b is 150, 100. So I'm going to get 1, negative 1, negative 1, 2 times 150, 100. So this part, so here is my a, and I've multiplied by a inverse, right? So I've multiplied by the inverse, which, like we said, is playing the role of the reciprocal. So what we're doing here is the same thing that we did here. I have this equation, and I want to isolate the x, so I multiply both sides of the equation by the reciprocal of a. So I'm doing the same thing here. So here's my x, and I'm going to isolate the x by taking my original equation, which is this one, and multiplying both sides by the inverse of the matrix A, which is what we did here. Now if I check, I get, take this row, 1, negative 1, dot product with this, and I get 150 times 1 plus negative 1 times 100. Okay. And I'm going to take row 2, I get negative 1 times 150 plus 2 times 100. Right? So I'm doing the matrix multiplication. This row times this column gives me this first first entry. The second row times the same column is what I'm going to put here. When I say times, I mean it's the dot product. Okay? And I get 150 minus 100, which is 50. And I get 200 minus 150, which is another 50. Right? So I get 50, 50. And that's xy. So x is 50 and y is 50. Okay? So this is exactly the same result that we got previously for the number of bikes and the number of unicycles. So matrices and matrix inverses can be used to solve systems. And when you take linear algebra, most of the content of the linear algebra course is far beyond what we have time for in this class. Linear algebra is a beautiful subject with many very useful tools. You can talk about determinants, and later on, if you take multivariable calculus, you will see Jacobians, which are very closely related to determinants. You can look at determinants, and you can look at adjoints, you can look at the adjunct matrix, and you can do cofactors and minors and positive definite matrices, and you get all kinds of really beautiful and interesting and useful things. We don't have time for any of that. So what we want to focus on is matrix multiplication. I'm going to ask you how to do some matrix multiplication, 2 by 2, maybe a 3 by 3. 2 by 2 matrix times a 2 by 2 matrix, or 3 by 3 by 3 by 3. So low dimensional stuff, not huge computations, but I might ask you just to do some matrix multiplication. You're going to have to show your work because, I mean, you can just put in matrix multiplication in Google and it'll multiply those for you. Any decent calculator can multiply matrices. We don't want you to use your calculator for all these problems, so you're going to have to show your work when you do the matrix multiplication. You're also going to have to compute inverses of 2 by 2 matrices, so we don't have the capacity to talk about inverses of 3 by 3. It's very complicated to do inverses of large matrices, and well, 3 by 3 is not quite large, but it's already complicated, and then 4 by 4, 5 by 5, those are very complicated. You're always going to want to do in a computer or with a calculator to invert those larger matrices, but we can invert 2 by 2 matrices by hand. So let me mention that now. Let's say we have a matrix, 2 by 2 matrix. The entries are A, B, C, D. A has an inverse if and only if AD minus BC is not equal to 0. Okay? So, just like not every number has a reciprocal, not every matrix, not even every square matrix, has an inverse matrix. So the only number without a reciprocal is 0, but you have lots more matrices that don't have inverses. So I have 2 by 2 matrices. They don't necessarily have an inverse, even if they have some non-zero entries. So if I have a 2 by 2 matrix, I can check whether or not it has an inverse by looking at this number. So this number is, well, let me write it this way so I don't mess up my original. So what I do is I take A times D, and I do C times B, or B times C. So I have a down arrow and an up arrow, and I multiply across each arrow, so the A and D, they're on the same arrow, the C and B, they're on the same arrow, so those things get multiplied. Down arrows get over here, end up over here with a plus sign. Up arrows, so the AD is a down arrow, so I could put a plus sign here. Up arrow is with a minus sign, so put a minus sign there. And that is this quantity. So you might want to think about this more as a procedure than just a memorized formula, or you can just memorize this formula, it's not too bad. Right? So this matrix is going to have an inverse if and only if this number is not 0, and if this number isn't 0, then the inverse of A is, well, I'm going to divide by this number. So I couldn't divide by that number if it were equal to 0. And I'm going to have dA. So just like before, I take the A and the D and I switch places. Okay, so I did that on the previous page when I computed the inverse of the 2, 1, 1, 1 matrix. Is I took the top left and bottom right entry and I switched them. And now the B and the C, I'm not going to move them, but I will multiply them by -1. Okay, so I have this matrix over here. I want to know whether or not it's actually invertible, so I check this number. If this number, A times D minus C times B, if that number is 0, then the matrix is not invertible. If that number is anything other than 0, then it is invertible, and this is the inverse. Okay. So this is a pretty useful formula for inverting 2 by 2 matrices, and I'll probably ask you to do that, and I'll ask you to show your work. So one last thing to look at is the transpose of a matrix. Okay. So the transpose of a matrix. So A is an M by N matrix. The transpose of A is the N by M matrix. So if A is an m by n matrix, then the transpose of A is the n by m matrix that I get by taking all the rows of A and making them the columns of a new matrix, right? So I'll explain exactly what I mean by that in an example in just a second. So we denote the transpose of A by a, here I'm going to put a capital T. Okay, so if A is a matrix, then A transpose is a different, well, possibly different matrix, and I denote it by A superscript T. Some people use A superscript little t, and some people use A prime. This is pretty rare in my experience, but statisticians love this. Okay, so in statistics a lot you see the prime notation for a transpose, but I'm going to use the capital T here. Let's look at an example. A equals 1, 2, 3, 4, 5, 6. Okay, so this is a 2 by 3 matrix because it has 2 rows and 3 columns. Okay. A transpose is going to be a 3 by 2 matrix. Right? So if A is 2 by 3, then the transpose is 3 by 2. What I'm going to do is I'm going to take the first row, which is 1, 3, 5, and make that the first column here. Okay? Then we take the second row, which is 2, 4, 6, and make that the second column here. So I take all the rows and make them the columns of the transpose. That's it. Okay. So you might wonder why this is important. Well, so I'm going to say if X is a, I'm going to say 3 by 1 vector, so if X is a column vector with 3 entries, I'm going to put an arrow over it so we can see it's a vector. And if Y is a 2 by 1 vector, okay, well, so let's think about this. A times X, well, A is 2 by 3, X is 3 by 1, that means A times X is 2 by 1. Okay, so this is a 2 by 1 vector, and I can take the dot product of it with another 2 by 1 vector, such as Y. Now if I take A transpose, which is 3 by 2, I can multiply it by Y. So if I take a 3 by 2 matrix and multiply it by a 2 by 1 matrix, I'm going to get 3 by 2 matrix, so I get A transpose Y. That's going to be a 3 by 1 matrix. Okay. And if it's 3 by 1, I can dot product it with X. And the transpose of A has the special property that, well, when I do these things, they're equal. So I choose X, and X has to be the right dimensions so that multiplication of A and X is defined. Right? So if A is 2 by 3, then X has to be 3 by 1 in order for this multiplication to be defined. Right? And if the transpose is 3 by 2, that means Y has to be 2 by 1 in order for this to be defined, this A transpose Y. But now, in my mind, what I think of is I'm moving the A from the X to the Y, but when I do it, it picks up the transpose. Okay? This is not only a property of the transpose, but a characterization of it. But I think the fact that I'm moving the A over here is the transpose. This is the reason that the transpose of a matrix is important. Okay? So if I ask you to compute a transpose, it's very, very easy. Take the rows and make a new matrix. The columns of the new matrix are the rows of the old matrix. That's it. That's the transpose. Okay? The reason it's important is because of this part over here. If you take linear algebra, that might come up again, but for us, this is not going to really come up. But I'm mentioning it because without it, you might not see any reason why the transpose matters at all. And that is it for matrices.